Swayam Prabha. Digital India. Educated India.
So, good afternoon. This is lecture number 24, fourth module, matrix analysis of structures with axial elements. If you recall, we had shown how the conventional stiffness method can be applied to problems with axial elements, right. This included 1D structures, it also included plane trusses, but space trusses we did not do because we said we would, they are complicated and we would show how you can use the reduced stiffness method to apply to space trusses. We will cover this in two sessions. In today's session we will look at the application of reduced stiffness method to 1D structures and plane trusses. So, this is covered in the fourth chapter of the book on advanced structural analysis. This slide is familiar to you. We are looking now at the reduced element stiffness method. What is the need for this method? Well, this is not a method that is used in softwares. This is a method that is often taught in universities because it is simple to apply, it is good for small problems, but it can be equally applied without any loss in accuracy to very large problems. It is not all that suitable for generalizing, but it is worth knowing how these simplifications can be made. Now, if you look at the genesis of this method, the conventional stiffness matrix for any element does not have an inverse, it is singular. Why is it singular? Its rank is not full. For example, typically if you take a space truss element in the conventional stiffness method, how many degrees of freedom do you have? What is the degree of, what is the size of the matrix? Space truss element, at each end you can have 3 independent degrees of freedom. So, it will be 6 by 6, it will be 6 by 6, okay. So, you will be dealing with big matrices and it is difficult to do, but if you, what is the rank of that matrix? It is only 1, it is only 1. So, you see it is how simple it is to reduce the computational work and use the reduced element stiffness method. So, that is the real use of this method. Not only that, if you are comfortable with this method, flexibility method will be easy to understand because the matrix that you get from the reduced element stiffness method, if you invert that matrix, it is invertible, you will end up with a flexibility matrix. Okay. So, we have done a review of this, but let us look at these applications. You can use it for a truss element, you have 1 degree of freedom. You can use it for a beam element, 2 degrees of freedom. You can use it for a plane frame element, 3 degrees of freedom, and so on. Okay. We are now looking at applications to axial systems. This slide again is familiar to you. Here you need to first generate the displacement transformation matrix, which relates the global coordinates, the global displacements to the element level displacements. Then you have the this matrix which is called the unassembled stiffness matrix in the local axis. What is the nature of this matrix? Remember there is a tilde here, it is K star tilde, it is a diagonal matrices where you just lump together in the diagonal all the different element stiffness matrices. Then you know that there is a contra-gradient principle which shows a relationship between the element level forces and the structure level forces, and then you have this transformation TD transpose K star TD, which gives you the structure stiffness matrix. Okay. This structure stiffness matrix that you get using the reduced element formulation is the same structure stiffness matrix that you would get had you done it by the conventional stiffness method. So there is no loss in accuracy, it is just that you have the advantage of dealing with smaller sized element stiffness matrices. So this procedure we have gone through earlier, but it will really make sense when we apply it to specific problems. So let us take the simplest type of problem. Well, in all types of problems, whether we deal with 1D structures, plane stresses or space stresses, you are dealing with this element. Now it has only one degree of freedom, and you can interpret that displacement as the elongation in the element. Okay, d1 star is nothing but the elongation in the element. You can even eliminate that 1 because there is only, it is a 1 by 1 element stiffness matrix, but it is left to you. And the only problem with this element is you can't discriminate between variations in end forces at the two ends. You can have only a constant element force in this as shown here. So the first question that arises is, how do you generate your TD matrix? You remember there is a kinematic way of doing it. You just have to remember it is minus cos theta minus sin theta plus cos theta plus sin theta. Remember this, we have done this. That means you keep applying a unit displacement at a time in your structure and see what happens at your element level. You can generate the same element stiffness matrix using a static formulation, using the TD transpose matrix. You remember this. In this procedure what we say is, if you have a unit force in the element, say unit tension here, then necessarily at the two ends you need external forces to satisfy equilibrium, and the relationship between the element level force and the end joint level forces is given by this matrix, which is TD transpose. But you really do not need this, since you know that it is minus cos theta minus sin theta plus cos theta plus sin theta. Okay. Next, if you have intermediate loads or say lack of fit or a temperature effect that you need to take care of in a truss or an axial element, we have to do this transpose. Remember we did this in the conventional stiffness method. Now the question I want to ask you is, can we do the same thing in the reduced element stiffness formulation, or is there a problem? The first problem we did was two axial elements, non-prismatic, connected to each other with some intermediate loads in both of them, right. Then we reduced them to equivalent joint loads using this transformation, right. We arrested all the degrees of freedom, found the forces, then we did TD transpose and got the structure level force. Can we do the same thing here, or do you see a problem? Is the question clear? Or we can do it? Will this TD transpose work? The answer is no. Now can you tell me why it won't work? Let me show you the problem. Let us take that same problem which we did. It was something like this, right. You had some distributed load, you had a concentrated load, you had 1 degree of freedom here, 1, this was element 1, this was element 2, let us say this load is Q and this load is P. We somehow want to reduce this to a problem where you have only one force here which we called F1, right. So what did we do? We arrested all the degrees of freedom. Remember you had 2 here and 3 here, and we found that Q into this length divided by 2 is the force that you get at the 2 ends, and P into B by L and A by L, remember that. So you got the element level forces, and then we had to transfer them to the structure level forces. Take this for example. You have an element here, you arrest this degree of freedom, arrest this degree of freedom. If you apply a force here P, this distance is A, this distance is B, this length is L, we know that you will end up with a force here which is PB by L, PA by L, right. And so you can write, let us say this is the ith element, you can write F ith element star F, okay. We could do it, how do you write this? Supposing this had 2 degrees of freedom, if you had 2 degrees of freedom, then you could have written this as, remember in the conventional stiffness method we had 1 star, 2 star, right. And so it was possible to write this as minus P B by L minus P A by L. That was possible. You could accommodate 2 different values here. But now we have a problem, because we have, unfortunately, in the reduced element stiffness method we have only 1 degree of freedom, and so our element is like this. We say we arrest this, this is pinned, and maybe you can, since you were uncomfortable in the last class not having a support there, put a support there, right, and this is 1 star. So I do not have 2 numbers here, I just have 1. And what is the axial force in this due to this? I have a problem, because the axial force in this element actually has a variation, right. In this region I get tension, in that region, so remember it was something like that. This is the axial force variation, okay. This is tension and this is compression. This was PB by L, PA by L, and so I can have different values, different signs if I had 2 degrees of freedom, but here I can have only 1 value, and I have to have uniform tension or uniform compression.
But the TD will be different for this.
Whatever I do, there is no way I can express a variation. This allows only a constant force in my element. This allows for a variation, okay. So that is a limitation, that is a limitation. So be careful when you use this formulation. Normally in trusses you do not have a problem because you do not have intermediate loads, but in beams you will get, in frames you will get, in axial elements you will get. So
we can treat it as 2 elements, and
yeah, then you are doing extra work. But if you had a UDL you can't treat it as 2 elements, you will have to treat this as infinite elements, so it does not work, okay. So intermediate axial loading in an element can introduce different axial forces at the 2 ends, that is the axial force varies along the length of the element. This cannot be accounted for in the reduced element stiffness formulation, in which Fi star can account only for a constant axial force in the element. So the transformation with TD transpose is not applicable in such cases. It is applicable, however, when you have a lack of fit or you have a temperature problem, because then it will be constant. So the problem is only when you have intermediate load, but otherwise you can handle it. So in trusses you can normally do it. In the latter case, when intermediate axial loading is present in axial elements, in the former case, when intermediate axial loading is present in axial elements, the fixed end axial forces Fi star F and the net force vector on the structure Fa minus Faf need to be assessed manually and given as input load data. So that is the only change. So whatever you are getting in the structure, do not use TD transpose and shift from element level fixed end forces to structure equivalent joint loads, do it manually. Let us demonstrate with an example. So we will take this very problem which we had already solved using the conventional stiffness method. Okay. What is the procedure? Well, first you have to find out the TD matrix, then somehow you must get the equivalent joint loads, which we will soon demonstrate, but you have to do it manually, you can't use TD transpose. Then you write down the element stiffness matrix for the elements and generate the structure stiffness matrix. The structure stiffness matrix that you generate by this method will be identical to the one that you solved by the earlier method. You find displacements and support reactions. This part is common to both the methods, okay, because once you have got the structure stiffness matrix and you have got the loads, you can find the displacements and then you find the member forces. Okay. Remember, when you are using reduced stiffness method, use a different notation for your element stiffness matrix, K tilde, that little curly thing on top of K, that is how you distinguish. Okay. And again, remember, if you have distributed axial loading, that is the part that you have to manually superpose. So I want you to see this one problem and you will get to understand how it works. First, coordinate transformation. Okay, we will choose the same global coordinates as we did when we did this problem by the conventional stiffness method. Only one active degree of freedom 1 and 2 restrained degrees of freedom 2 and 3. As far as the element is concerned, only one element coordinate 1 star 1 star, whether it is element 1 or it is element 2. Can you write down the TD matrix for these two elements? Please try it. So we are trying to find out what happens to the two elements when we apply D1 equal to 1, when we apply D2 equal to 1, when we apply D3 equal to 1. Write down the TD matrix by the element stiffness method. So I will help you. Now this is what you will get. Okay, let us see what is happening. If I pull this joint to the right, I get D1 equal to 1, but I do not allow D2 or D3 to have a non-zero value. When I do this, what will be the elongation in member 1? It will be plus 1 or minus 1? Plus 1, right? What will be the elongation in member 2? Minus 1. It will go into contraction, right, because you are pushing it to the right, this, and you are not allowing D3 to move. So this first column that I get, when I apply D1 equal to 1, I get plus 1 as nothing but the elongation in element 1 and minus 1 in the element 2. Is this clear? Makes sense? Okay. Now you apply D2 equal to 1, but D1 is 0 and D3 is 0. What will happen? Only this element will get affected. What is the movement in that? What is the elongation? Minus 1. So you get minus 1 here and 0 here. Lastly, when you pull D3 equal to 1, element 2 will get elongated. So, and element 1 remains unaffected, so it is 0 1. Is this clear? It is as simple as that. In 1D structures, you will have only zeros and ones. No sin theta cos theta here because theta is 0. Is it clear? It is very easy. I hope there is no confusion here. It is straightforward. Okay. Next, so you can put it all together in one matrix. You need not write TD1 and TD2 separately. For small problems, it is nice to deal with one full TD matrix. Is it clear? Okay. As far as fixed end forces are concerned, we have done this earlier. Remember, we had to convert the intermediate loads to the end loads, and this we have looked at earlier. Remember this? So I am not going to repeat this part. This part is well known. But here we have this problem that I talked about, the problem of how to handle this situation. Well, you can't handle it if you have only 1 degree of freedom per element. So you forget about how to handle it in a mathematical framework, just put it all together manually and tell me what F1 and F2 and F3 are going to be. What are the equivalent joint loads due to the intermediate loading? Can you tell me what F1 is? F1F. See, all that we are saying is F is equal to TD transpose F star F. You can't do for reasons we have already discussed. So do not do it and just give me directly this value, which means what is F1F, and you can partition it like what is F2F. Can you give me these 3 values just by looking at that diagram? Tell me.
40, 20,
Huh?
minus 40,
This is minus 40,
minus 20,
this is minus 20,
minus 10.
minus 10. That's it. That's it. Now remember, there was a nodal load in the structure. There was a nodal load in the structure. Let us go back to the original. Remember, there was a 40 kilonewton acting at F1. So that you have to include. So you have to do it the good old way, and you will write it like this. So this is what we discussed. Manually do it. You will end up with the same displacements as you would get in the original structure, but now you also have to add FA is already there, so we will use that later. You have to finally, your net load vector is FA minus FF. Why do you put a minus? Yeah, because you have to reverse the load that accumulates at the artificially arrested locations. So that is why you have to, the equivalent joint load manifests as with a minus sign. We have done this earlier in the conventional stiffness method. So this step is clear to you, you said it right. Now let us generate the element and structure stiffness matrix. How do we do that? You have got TD, you need K star. What is K star? Well, you have 2 elements. For each of the element, the K is nothing but the axial stiffness, which is EA by L. For the first element, EA is 2 EA and the length is 2 meters. For the second element, EA is the axial rigidity, the length is 3. Okay, so you have got this. How will you put it all together in one matrix? Okay, well, you can put it all together later. I will show you another way of doing it, but if you leave it like that, we can do this calculation. You post multiply K star with TD, right? Will you get this? Because you just have to carry out that operation. Then you do pre-multiply with TD transpose and you will get the final answer. You do it for 2 elements. You understand, each element is contributing to the structure stiffness matrix. So then what do? How do I get the total matrix? Just add. I mean, you've got this contribution, add it up numerically and you will get the final matrix. Does this make sense? Very easy to do. Small matrices, you do not even need MATLAB and all that, manually you can do this. Is this clear? It is a simple problem. If you want to handle everything in one go rather than do superposition, that is also possible. This element by element approach is sometimes called the direct stiffness approach, but you can do it alternatively by taking the full K star diagonal matrix, the full TD matrix and do the same operation, go through these steps and you will get the same matrix. Is it clear? Two ways of doing it. Do it element by element, add up their contributions in the structure stiffness matrix, or do it in one shot. It is worth doing it in one shot if your sizes are small. If sizes are large, you have say 20 elements, then it is not that easy. Okay, it is better to do it element by element, also your storage becomes much easier. Okay, so we have got up to this stage. Now mind you, you are getting the same matrix you got earlier. In conventional stiffness method you had more degrees of freedom per element, now you have much less, and KAA is just 4 by 3 EA. Find the inverse of that and the rest of it follows. We have done exactly the same thing. I hope these equilibrium equations are familiar to you. You solve the first equation and you will get D1. Remember we got 12 mm last time, it is the same thing. This part from here onwards it is similar. To find the member forces, of course you have okay, these are the support reactions, you get the support reactions also. How do you get them? From the second equation. Remember, use the first equation to solve for dA and use the second equation to solve for FR. We did this earlier, it is nothing new. So you do that and you will get the support reactions. Then you get the member forces. It is here that you have to be careful because you have to do it manually because you are getting two different member forces. So you do it carefully and find, you have to add, see you will get this constant force from your matrix analysis, right. We got these values 60 and 20, but you have to add what you got, the distributed force which you got manually, and then that is how you get the total axial force distribution, which will look like this. It is the same answer that we got earlier. Is this clear? And you can also get displacements. Second example, this also I think we did by the conventional stiffness method. Here, any questions? Okay. Here there is no axial load, there is only indirect loading. You have a temperature rise of 40 degrees Celsius in AB and 20 degrees in BD. The coefficient of thermal expansion is given to you. You also have support slips to the right of 2 mm and 1 mm at A and D. Okay. Same problem we did earlier, let us do it by this method. Here can you use the TD transpose to get your equivalent joint loads? Yes, yes, because you have a uniform force, there is no variation here. So here you can conveniently do it. So you must use the right technique at the right place and not get mixed up. So the input data is this, it is indirect loading, change in temperature and support slips. Okay. So how do you deal with the change in temperature? You take your primary structure, do not allow any movement, and you will find that when you raise the temperature you will get some axial compression in both the members. That gives you your internal forces and that is how you work out. So the steps are similar, only thing your axial force will have minus EA by L into E, and the steps are exactly identical. We put a delta for delta FF because we are saying that when you have indirect loading, this is an additional effect that we include, and so we put that capital delta. Is it clear? Rest of it is same. So you have the same coordinates, we do not waste time, we have already generated the TD matrix, it is the same structure and the same K matrix. You have already done the stiffness matrix, it is only the loading that is going to change. So how do we take care of the loading? First find out the free elongation L alpha delta T, right, and that elongation is fully prevented in the primary structure. So is this step clear? You get that much, that is E naught. Now if you have a lack of fit problem, you get E naught directly, you do not have to do this step of L alpha delta T. You got E naught and then you know that this will induce axial compression of 44 and 11 kilonewton. We got these numbers last time also, remember. In the first element you get a 44 kilonewton compression, second element you get 11 kilonewton compression. So you can do this calculation directly. Always use your common sense, do not use formulas. you should get a feel for the problem. Yes, this makes sense. Do not put plus 44 and plus 11, and you have only one force per element because you have only 1 degree of freedom. Is this clear? This you can handle. Then you can, like we did by inspection, fill up this, or you can do it by TD transpose. It both will work, you can check it out. But in any case, you have 44 and 11, they will add up together at D1, you will end up with minus 33, and you will have 44 and 11. Is it clear? F1, F2, F3 will have these numbers. Thereafter it is a straightforward, using matrix methods, you solve this, you will find dA, you get 6.7 mm, find the forces. Remember we did this problem, you got the same answers, 20.5 kilonewton, and so you can get, you have got your reactions. If you want to see how it will change shape, this is how it will change shape. The left end moves to the right by 2 mm, that is input, the right end moves to the right by 1 mm, and D1 has moved 6.7 mm. And if you want to find the member forces, same procedure, that is it, you have got everything. You have got the internal forces, it is a constant internal force even though you have a non-prismatic element, because that is the only way you can satisfy equilibrium. Both elements will push each other and the force is 20.5 kilonewton. This is how the displacement change. Are you comfortable with this? You have to do a similar problem in your assignment. Okay. So as obtained earlier, same solution. Now let's take a truss. Okay. Let's do it together. Did we do this truss by the conventional stiffness method? No. So we are doing it first time. Just take down this truss. You have 5 bars and you are given an applied load of 100 kilonewton at C, and you are told that the bar 4 is too short by 2.5 mm. Okay, so it is a complete problem. How do we do it? Let us do it slowly together. First tell me what are the, how will you express the input data given? How will you express the loads given? What is the first thing you need to do? You have to assign the coordinates. So shall we do that? So how many active degrees of freedom do we have?
4.
5.
You have a roller support which can roll. Roller support can roll, agreed? So 5, okay, if you said 4 you got it wrong. 5 you can number them any way you want, but usually along the x direction 1, along the y direction 2. Is this clear? You got it? Fine. Okay. Then so you have got 5 global coordinates. These are active. What about the restrained ones?
3.
So you can mark them also. Okay. Now let us say the question is, what was the question? You got 3 only, no? You got 4, you are right, the spring force will also push at the right end, so you got 4. You have 7, 8, 6, 7, 8, 9, right. Now mind you, this is essentially a manual kind of method. The reduced element stiffness method, you have to use a little bit of your brain to help you solve the problem. The support reactions are very easy to calculate, right. So if you had to find only the bar forces, you need to actually generate only the KAA matrix, right. You do not need the KAR, you do not need KRA, you do not need KRR. So if you go back to the original question was just find the bar forces. So let us do the minimum work required to solve this problem. So what do we do now? Now we have to deal with each element. So you need the local coordinates of the element, and first you write the input data. What is the input data? F3, because we chose 1, 2, 3, 4, 5 active coordinates. Only F3 is non-zero. There is a load, it is plus 100 kilonewton, agreed? Then you have an initial elongation because the bar 4 was given to be too short by 2.5 mm. So, how do you write that? E naught 4 is minus 0.0025 meters. Does it make sense? That was given to you. Okay. Now the local coordinates. Just draw a general picture like that. That is a typical local coordinate. Is it fine? 1 degree of freedom per element, and you can put a theta, and you have covered all the 6 elements. The spring also you can treat as a 6th element. What is the difference between a spring and a truss element? Absolutely no difference. It can also take axial tension. So, it is just to frighten you, do not get frightened. That curly thing you can straighten out and just put an element there, call it number 6. There is nothing great about that. Is it clear? Okay. Now what do we do next? You have to generate the TD matrix. Okay. How do you generate the TD matrix? Please generate the TD matrix. Please generate the TD matrix for this truss. You have how many elements? You have 6 elements. Generate the TD matrix. Well, maybe it will help us if we make a small table, right. This is especially useful when you have large trusses, but in this problem you could have directly done it. So, this is a conventional style. Identify the element number, the start node, give it some coordinates, the end node, the length of the element, and cos theta can be easily written as, you know that, x end node minus x start node divided by length of the element. So, let us say we have done this exercise, okay, and the stiffness also is given EA by L. So, I am giving you this table because that is easy to do. With the help of this table, now generate the TD matrix. Okay, you can pick up cos theta sin theta from here. Will you do that? Okay, while you do that, let me review the procedure. First you have to get the TD matrix. It is enough to get TDA because we are not interested in the reactions and all that. TDA is all that you need. Then you generate the structure stiffness matrix, find the fixed end forces. You have, as we are required to find only the bar forces and not the support reactions in this problem, and as there are no support movements, we can ignore the restrained global coordinates 6, 7, 8, 9. Find the displacements and find the bar forces. The lack of fit in bar 4 will generate a fixed end force in this bar, which you can calculate, and all other fixed end force components in F star F will be 0. This is all obvious from the problem. Okay. Now, you want to get the TD matrix. Let me help you with this. You have got this. This is all that you need, right? That big table I made it simple. Generate the TD matrix. TDA matrix, right? Again, to help you, this is the formula. If you have the two ends and you had coordinates 1, 2, 3, 4, actually the coordinates will be different. They will be numbered arbitrarily. But you have got cos theta sin theta. Can you now using this information generate the TDA matrix? It is not difficult. Let me give you a clue and let me close it. You have 6 elements, For each element, what is the size of the TDA matrix? Why do you say 4? This is for the whole structure. How many active degrees of freedom are there? 5. So it is going to be 1 row, 1 by 5, 1 by 5, generate. It is 1 by 5. And there are 6 elements. So it totally will be 6 by 5. I want to see that 6 by 5. You have to do it. You got all the sin thetas and cos thetas here. Just move your brain. Some of you are too tired. Wake him up. Please do this. You want me to show you the answer? You will give it a shot? We do not have too much time, I will give you 1 more minute. But if you do one problem, you will see that it is very easy, it is not difficult. The axial system was very easy because you had only 0, 1. Now you have this cos theta, sin theta coming into play, but there is a method in the madness. Your actual TD matrix, what is the full size if you include TDA and TDR? How many columns will you have? You will have 9, 5 belonging to active degrees, 4 belonging to the. So you will have mostly zeros and you will have this 4 non-zero quantities, cos theta, minus sin theta, plus cos theta, plus sin theta. So each row will fill up 4 locations, the rest will be 0. You understand? I will give you an example. Take this element, element number 1. Element number 1 will have values in the first row because this is there, D1 is there, the second row, the 7th row and the 8th row. Of course 7 and 8 do not come in TDA, right. So it will fill up only in 1 and 2. What values will you put for 1 and 2? Will you put minus minus or will you put plus plus? Why?
It belongs to 1, 2, 3, 4.
No, it depends on your angle of incidence. Which is your start node, which is your end. Look at this element. In this element, my local x star axis was pointing from here, right. That means this left end was my start node, this right end was my end node, right. Do you get what I am saying? So you have to identify which is start and end, then only you can do it. So which means you have to go back to this. So let us go through it once more. Element 1, the start node is A, the end node is B, x star, local x star is moving that way. Element 2 from D to C, element 3 from A to C, element 4 from D to B, okay, and element 5 from B to C, and element 6 from D to E. Is it clear? Because if you reverse, then theta changes. Do you understand? So let's go through the solution. Okay. This first row, okay, let's take element number 1. Element number 1 will have only positive values, it will not have negative values because these two will go to 7 and 8. 7 and 8 do not come in TDA, is it clear? So you just copy down 0, 1 to the first and second row. Let us look at the 4th element, okay, this is the 4th element. 4th element starts here and goes there, So 5, which is 5? 5 is active, okay, 5 is active, and here you will put 5 and 6. So 5 will be minus cos theta and 6 will be minus sin theta. So minus cos theta is this, you get minus of minus is plus 0.6, got it? Didn't get it? Okay. Careful, listen carefully. Let me explain on the board. This is the only tricky thing. Once you've got this, everything will move smoothly. This was the element number 5. 5? Was it 5? 4. Element number 4. This was the incidence of x star. Okay? This was the incidence of x star, which means that if this is my positive x axis, this is my definition of theta 4x. So this is start node, this is end node. Okay. Now what are the structure coordinates here and here, here and here? What are the structure, what are those numbers? What is this number? 5. What is this number? 6. But it's kind of a restraint code. What is this number?
1.
1. What is this number?
2.
Got it? So if I had to write TD for the element 4, I have to fill up a vector like this, of which the first 5 will correspond to T4dA and the next will correspond to T4dR. Got it? Now, so this has got 5 parts, am I right? So 1, 2, 3, 4, 5. So here I will fill up for D1, here D2, etc., etc. So this is 3, this is 4, this is 5, this is 6, this is 7, this is 8, this is 9, right? Okay, if I may remove this. Now how do I fill up? Which will be 0 and which will not be 0? I've got this is 6 and this is 5. So let's be very clear. I'll have a non-zero value here. So let me put a tick here, right? D5, D6, these will be there, and I'll have 1 and 2, and the rest will be 0. So let me go ahead and put the zeros so that my life becomes easier. Is this clear? Now I have to decide what to, I have to put in these numbers. I have to put in minus cos theta, this is 4x, minus sin theta 4x, plus cos theta 4x, and plus sin theta, right? This is how it goes. These two will go to the start node always, that is how it is defined, and these two will go to the end node, right? You just go back to the derivation. Now, so here I should put, so let me simplify and put minus C4. Here I should put S4. Here I should put
C4.
plus C4. Does this make sense? You can program it, it will do it automatically. Now do these answers match? Because take a look here, C4 is minus 0.6, S4 is plus 0.8. Does this make sense? Now this will fill up the whole vector, that is TdA and TdR. If you want you can fill up TdR, but we do not really need TdR. So can we fill up this TdA matrix? Can you do it correctly without making any error? Any doubt? Ask.
In second element,
In second element, yes.
what is the start node?
Okay.
D.
In the second element it is going up D to C. D to C. Oh, you can choose anything you want. How to you mean? Is there a golden rule? There is no golden rule. I like going from bottom to top. If you want to go down from top to bottom, that is all. There is nothing, no sanctity in all that. Sorry? So let's, I think I went through that step. For first element, from here to there. Second element, from here to there. Third element, from here to there. Fourth element, from here to there. Fifth element, from B to C. Now you are asking why not switch everything upside down? You are welcome, but be consistent. So in the first table you do it correctly, but the incidence is very important, otherwise you can't use blindly these formulas. Otherwise you figure it out yourself. You can also use the TD transpose and use static method and get it, but this is a kind of blind method which will always work. Have you understood? Can I proceed? Clear? Just go through this problem carefully. If you get it once and you solve the assignment problem, you will understand. So I can put it all in one box directly like this. Yeah.
Be consistent in ordering. Basically, what is the order? You can go from left to right and then.
You can go any way, but your cos theta, your theta will be defined with respect to the positive x axis. Supposing this was my start node, my theta would have become like this. That is the definition of orientation, isn't it? So see, this was my direction, this was my x star axis. Supposing I choose this as my start node, then my theta x would be, this is my positive global x direction, it will go like this becomes theta x, which is different from this theta x. Got it? See, we are talking of direction cosine. So we said cos theta Ix is always x end node of the element I minus x start node of the element I divided by the length of the element I. This is the direction cosine definition. Similarly, sin theta will be with respect to y axis, this x will be replaced by y. So it is easy to program, you do not have to worry, you do not have to break your head about minus and plus, it will do it automatically and beautifully. But once you have decided on the direction of incidence, which is your start and end, you better stick to it. You don't change your game plan in between. So it follows very nicely. Clear? Can we move on? We will just finish this. So now you have got the TD matrix, please do it correctly, but it is not difficult. Just do a couple of problems, you will get the hang of it. Then you can assemble you have got the stiffness matrix, you have got EA, you have got L, you can all put it together this way. Is it clear? It is a diagonal matrix. If I have not filled up anything else, it means it is all 0. So this is my K tilde star matrix, okay? Clear? Because you will get it from your axial stiffness for the 6 elements. Then what? Then I have to generate my structural stiffness matrix. There are two ways of doing it. It is actually TdA transpose K star tilde into TdA. I can do the latter part first or the former part first. It is better to do it this way because this comes in handy to find my member forces. So all this is best done using MATLAB or some but if you want to do it manually you can work out, it is not all that difficult. So once you have TdA and you have got this, can you do this product? Easy, you get this, then you pre-multiply it with this, in one shot you got the final structure stiffness matrix. it's a 5 by 5, it's a square matrix, it's a symmetric matrix. Got it? Got it? Clear? Now what? Now invert it, or you can use Gauss elimination. Now you are ready to handle any loading that can come on the structure. Any loading can be handled. This is a property of the structure. So it's ready. Once you give the geometry, give the EA by L values, you can program your system for you to generate the element stiffness, the structure stiffness matrix. Then you find your fixed end forces. Here one of the elements is too short. So remember how to do this. See, the axial force in that element is always minus of K E naught. K for that element axial stiffness EA by L is given, E naught 4 is given, so you get 200 kilonewton. Okay, minus of minus is plus, which means if the element was too short in the primary structure, you had to stretch it to fit it to the two ends. That's why you will get tension initially. Does it make sense? Physically, does it make sense why you get a positive quantity 200 kilonewton? The element came too short. In your primary structure, the ends are locked in the original configuration. So you got to stretch this element to lock it there. So you will get a tension, which is nothing but axial stiffness into that initial shortness in length. Got it? So you will get this F star F. Then if you do TD transpose, mind you there is only one non-zero F star F, you will get, you are converting what happens to the joints. You know, this has to pass on to the joints in the structure. You do not have to break your head and figure out what happens, just do TD transpose, TDA transpose. So it's switched over from the element level to the structure level. Is it clear? We did it for the axial system, the same logic holds good for the structure. And then you have your equivalent joint loads. Remember, your original nodal loading is 100 kilonewton at F3, but you have this extra loading coming from that lack of fit. So this is FE minus FFA, this is called the final total joint load vector, FA minus FFA. You got a lot of loads now. Okay, only one of them is not 0, that is F4. Then what do you do? Then you find the unknown displacement. You got the load vector, you got the structure stiffness matrix, you inverted the Ka matrix, you do this operation, you will get the answer. You've got the answer, you've got the, then what do you do next after you've got the solutions? You've got the unknown displacement, but that's not what you really wanted, you wanted the bar forces. So to get the bar forces, you remember you've already computed this and you are ready, you got the initial bar forces, there is one 200 kilonewton already there, this FFA, remember, and then you do this operation, you get these answers. And if you want, you can also find the support reaction if you bring in TD R into picture. That is it, one problem, understand fully, and you can handle it. Tomorrow I will take a really bigger problem, a 10 bar truss, a compound truss, just to demonstrate, and we will close and we will do a space truss. Thank you.